Welcome, geologist, and we will be embarking on the beginning of a 4.6 billion year journey in this class. So up until now, you've learned about the history of geology, some of the important faces and names that shape the science and study of what we're learning about. You've learned about fossils and how we classify them, how we define their terminologies of assemblages, their preservation, their usefulness in stratigraphy and age dating in terms of relative dating. You've learned a little bit about absolute dating, which will be important to this lesson today. You've also learned a little bit about evolutionary trends and theories and how that applies to life and its origins on Earth, which will certainly become apparently clear during our Precambrian lessons. You've also learned a little bit about stratigraphic principles, things like law of superposition, law of original horizontality, law of inclusions, faunal succession. All of these things were the foundation for what we're fixing to learn in Hadean. You even learned about sloth sequences, which are important to understanding sea level rise, which will actually surface in our Proterozoic lesson for the Precambrian. So you're looking at the Black Hills of South Dakota here, and the Black Hills is just an incredibly beautiful place. It's right outside, well, it's part of Rapid City, South Dakota, but this area that is my favorite is in between Rapid City and Sturgis, South Dakota. And there are some Archean and Proterozoic rocks that are very, very famous, and one place in particular that you'll see as we go through our lessons on the Precambrian. So the Precambrian is a representation of the Earth's history before the Cambrian period. I know that may sound obvious, but there are a number of people who don't understand that everything that happened before the Cambrian is considered Precambrian. How much time does that constitute? If you're looking at 100% of geologic time, and let's put that to a football field, we're looking at the 88-yard line, from one end zone to the 88-yard line. That's how much time we're talking about. So that seems like we should have a pretty good volume of the Earth's record there, doesn't it? But the truth is we don't. We have a minimal rock record of the Precambrian, at least certainly for the Hadean, somewhat for the Archean, much better for the Proterozoic, which makes sense from oldest to youngest. So we're going to be looking at the initial inception birthday of the Earth, which is somewhere around 4.6 billion years old. To be clear, it's 4.54, depending on what you read, to 4.56 billion years of age. And so we're going to look at that age, and then we're going to kind of run through the scale and talk about what happened in the Hadean, Archean, and Proterozoic. In 1982, the North American Commission on Stratigraphic Terminology recommended that a formal designation be made to include divisions of time for the Earth's early history. So Archean and Proterozoic were first proposed, and an informal designation of Hadean referred to any rocks that were older than the rocks that we have found terrestrially on Earth. What that means is rocks that were generated on Earth, not meteorites. We certainly have meteorites that fall in the Hadean time frame of when they were incepted. So the rest of the time scale, starting in the Phanerozoic, is based on both absolute and relative dating, unlike the Precambrian, which is solely based on absolute dating. So we're using isotopic dating techniques such as potassium and argon and uranium to help us come up with absolute ages to the start and finish times of when these events occurred. So these are pretty standard in most time scales, that at least whenever we start the Precambrian and the Hadean, it goes to 4 billion years of age, so somewhere between 4.6 to 4.0 billion years, and then the Archean is 4.0 to 2.5 billion years, and then 2.5 billion years for the Proterozoic up until 542 million years, which is the marker that stops the Precambrian and moves into Phanerozoic. So we'll talk about why once we get to the Proterozoic eon. So how did the Earth initially come to be? If you could imagine a swirling eddy of gas, dust, much like we can see in the solar system today for brand new solar systems that are forming. As this material finally coalesced and it actually collapsed in on itself. This process of collapsing to make a definitive structure known as our sun probably happened over a short, brief geologic time period, which would have been about 10 million years. So if it's not 10, it would have been several tens of millions of years, a short duration, a glimpse of time. Once that occurred, solar wind began to blow out material from the newly formed sun, which would cause bombardment of pieces of material flying around, which would lead to the accretion and the formation of our first protoplanets. And so as more material struck these little planets, they began to grow in size and also their chemistry. So that's really important in the Hadean eon. So how old do we age date the Earth? We age date it to approximately 4.54 billion years. There is some literature that dates it as far back as 4.56 billion years. That's just a matter of just a slight difference in age. The point being is you could round up to 4.6 billion years. And that's where that rough estimate of 4.6 billion year old Earth comes from. Reality check is we haven't found any rocks that old on Earth that were generated on Earth, meaning terrestrial. So we have to look elsewhere for the answers. Two places that we're going to look. We went to our nearest neighbor, which was the moon, and picked up a few rocks and brought them back on the Apollo missions. That moon is thought to have come from planet Earth, so it should be slightly younger. So one of those dates, or the dates taken from the Apollo missions, helps us narrow the scope of the age of the Earth. The second place that we go to get that information is we look at meteorites. Meteorites that have fallen to Earth, and those date slightly older than the Earth at the beginning inception of the formation of the solar system. In all fairness, we have a third place that we can look, but that is a discussion that's fixing to occur. Let's get to the moon story, though. We can't really go any further without talking about how critically important the Apollo missions were. Really, the Apollo mission had one major objective when you think about where and when this occurred and in our past in terms of civilization. It was to find out answers about the moon, specifically the age of the moon, how did it get there, those types of questions. And the Apollo mission successfully answered most of those questions. We know that isotopes of tungsten and hafnium in lunar rocks have produced us with a very important age date for the moon. And the age date of the moon clocks in at 4.53 billion years old. So slightly younger than Earth. How do we know that? Besides dating it, we also can look at the chemistry of the magmatic material that came to make the moon. The moon just didn't happen to get into our orbit. It was caused by a bombardment with planet Earth. Now, when we look at meteorites that have fallen to Earth from the solar system's earliest days of being formed, they date back to 4.57 billion years old. So the sun must be slightly older than that as well, coming to the 4.6 billion year old thought process. In the Northwest Territories of Canada, the oldest known terrestrial rock has been found, and that dates at 4.0 billion-ish years old, the Acasta gneiss. And this is a very, very old rock. What is used in the rock to date are actual crystals that represent the initial cooling of the Earth from its Hadean heat. That's just the radiogenic heat that the Earth was giving off from the isotopic breakdown of minerals that make up the core, and some of its actual formation heat that actually occurred when it was being bombarded and accreted together. So these zircon crystals are kind of special because we have zircon crystals in most rocks today. Most of these have gone through many evolutionary changes in terms of series of metamorphisms, series of sedimentary changes, igneous changes, and so forth. So zircon crystals that have survived multiple episodes of these changes allow geologists to glimpse back into the Earth's history and kind of turn the clock back further to see what was going on. Here's what's really cool about zircons. Not only do they capture the metamorphic history, they kind of tell us when the first water came about. They tell us when the earth actually crystallized to make a crust. They give us all this really cool clues that other minerals just don't. So what is a zircon? When you look at its atomic structure, it's Zr and it's SiO4, which is its atomic number. And when you look at zircons, what's really important about it is in the cores of a zircon crystal, like you see right here, we can see when that actual crystal started to become crystallized. In other words, it started to grow as a crystal. That represents a place in the Earth's history where the crusts began to form, and that dates back to about 4.4 billion years old. One great thing about zircons is they're pretty resistant to weathering. Now, on the most hardness scale, they're not as hard as something like topaz or something like corundum or diamonds, but they're still nevertheless very, very durable. But what's important is they have a very, very hot crystallization point. And so that makes them stick around for quite a long time, and you don't find them in certain types of rocks. Like zircons are very rare in mafic and ultramafic rocks. And since they're so durable, what rocks we do find them in, they've hung out and give us these glimpses back into geologic past. The cores of zircons contain the oldest ages of the crystallization point of where this mineral occurred. So in other words, as the layers of crystals change, we can record multiple historical events, almost like a tree ring. So we use a certain type of technology. There's several types actually, but one common one is called TIMS, which is isotope dilution thermal ionization mass spectrometers. And this is a very, very precise testing method that uses an entire zircon crystal or a small number of smaller zircon crystal portions of that particular test sample dissolved in solution to analyze a composite uranium to lead age ratio. It's best used for rocks that cooled quickly, things like volcanic ashes. So if you get rocks that have been heavily heated, metamorphosed, or impacted in some kind of heavy pressure, they're really not a good fit for this. You need rocks that crystallize quickly. So in the Hadean, a couple of major things occur. The solar system forms. I think that's pretty newsworthy. And when we're talking about each geologic segment of time, a couple of things I want you to think about for test. Is it newsworthy enough to tell the front page story of what happened during that time? If so, it's probably a good test-related question. Did an orogeny first start a mountain building event? Did we have a major rifting event that occurred? That's pretty newsworthy. Did a new life form evolve or go extinct? These are all the types of things that are very important. Was there a major index fossil that we're going to cover? So this particular course is kind of a no-brainer as to what types of questions should be asked on an exam. You just have to learn the material. So that's the good news. So our terrestrial planets, which is Mercury, Venus, Earth, and Mars, accreted from planetesimals. And planetesimals are these small planet-like structures. So these planetesimals will be critical for helping Earth turn into the dynamo planet that it is. Let's talk a little bit about that dynamo process. As we're being bombarded by these smaller planetesimal structures, we're going to gain their composition. So most of the early stuff that came out of the sun was very rich in metals, and so we obtained that as these meteorites and planetesimals smashed into Earth, ultimately giving us the Earth that we know. So as the Earth receives this material, what's naturally going to happen is it's going to go through a differentiation process. It's a big word, differentiation, but one super important to our story, because differentiation means this. It means the more dense minerals will sink into the center of a structure, and their lighter weight elements will stay towards the top or float towards the top. So what that did for us is give us a layered Earth, bottom line. So our iron and nickel and heavy metals would sink to the interior core, and they're going to start their long-term breakdown of radioactive decay, which is one of the main processes of heat that gives off for the planet even today. But in this initial formation, we had just some of the basic Earth formation heat and friction from all that bombardment that occurred as well. So you can't forget that that heat still exists, or was much stronger back in the Hadean. We don't have that kind of heat today. So another important thing to point out about the Hadean is continental crust started to form about 4.4 billion years old. We know that because of zircons that I just mentioned earlier. Towards the end of the Hadean and at the very beginning of the Archean, we have a period called the Great Bombardment. This was a time when the Earth was being hammered. I might also add the Moon. Any terrestrial planet was being hammered by meteorites and planetesimals and things that were floating and being pushed out from the sun into our solar system. So that creates lots of bombardment, which will be important to helping finalize the Earth into what we know it today. So as the crust began to form, we are looking to zircons to tell us that story. They likely formed soon after the molten Earth solidified, which would have been approximately 4.4 billion years old. So when you think about when did crust start to stabilize, it may have been slightly later, but we started to see crystallization occur at 4.4 billion years of age. So if you see something like this 4113 MA, that stands for 4,113 years. In other words, we're looking at 4,000 million years approximately. And so you're looking at a very old zircon crystal, the core of it, that's over 4.1 billion years of age. It's pretty old. And so some of our oldest zircons date back much further than that, to right around the 4.4 billion year marker. So there is a moon giant impact theory, of which is generally accepted by most scientists as how we got what we call our neighboring structure in the sky called the moon. As the early Earth was being bombarded during the great bombardment period of time, where we're being smashed by all these things being thrusted in through the solar system, the Earth got struck with a planet much the size of what modern day Mars would look like. And when this happened, we were still molten. That's an important element. If we had crust, it was just starting to stabilize. And this caused a burst of gigantic amount of molten material and cloud of particles and dust to be ejected out into our orbit. And eventually this would congeal together, much like our dust cloud did that formed our planet and created our moon. So our moon is made up of particles primarily made up from Earth. The immense bombardment took millions of large objects that did not end just gradually. It actually had a finale. So a season finale occurred at the very beginning of the Archean around 3.9 billion years ago, and the source of the late bombardment is thought to have come from a specific event. The inner solar system was being thrusted by objects coming from Jovian planets as they stabilized their orbits. So the beginning of our bombardment started with the sun, and then the big planets kind of threw back stuff into the inner solar system, creating what we call the Great Bombardment. So it got hit and hammered for quite a while during the Great Bombardment. The moon's surface is good evidence of that bombardment. Differentiation, I can't underscore how important that is to the story of the Hadean, because the denser minerals that we received during the accretion process sank to the interior of the planet and the lighter ones rose up to the surface. So the heat that makes us go, that makes plate tectonics work, came from the initial formation of the Earth, in other words, radiogenic heat, and then radioactive decay, which ultimately would create mantle plumes and start what we would know as volcanism. And that process has been going on ever since. So volcanism, we know, began in the Hadean, and that's important to our story as well, because outgassing is a process by which volcanoes release water vapor and other gases and elements when they erupt. We know that water started to form during this time and accumulates as surface temperatures on Earth began to cool. This likely occurred somewhere around 4.4 billion years ago. How do we know this happened? We base it on oxygen ratios of O18 to O16 ratios in zircon crystals. So that indicates reactions with water. So zircons are clues not just to when the crust stabilized, but also when we were beginning to get the first water on the planet. Somewhere in the Hadean, it has to be that subduction began its process. The first crust was likely ultramafic. We know that even the deepest parts of the mantle are ultramafic. And so during the Hadean time frame, when the Earth was much hotter, that's pretty much what we should have been cranking out as ultramafic and mafic type rocks. So as mantle plumes started working their way up to the surface, as they upwelled, the first mafic magmas blended with the first crust, creating our first subduction zones, because when you get one crust that's more dense than another, the more dense one sinks into the mantle. So that begins this long journey of subduction that's going to create our protoplanets and ultimately the first continents that you and I know. Our first crust was likely ultramafic. Ultramafic is very low in silica and high in things like magnesium and iron. Well, as this occurred and we started to get blending of magma, so magmatic blending, as you learned in physical, is really important to different chemistries of a volcano. So these volcanic events that you would get mantle plumes known as hotspots working their way up towards the surface were likely bringing ultramafic and mafic rocks to the surface. As those blended and created new chemistries, we began to have more dense material hitting less dense material, creating our first subduction zones. And probably this would lead to the formation of our first island arcs. Since most island arcs are created very similar to this way today, we believe that's how the first island arcs were made, was through initial blending of magma. We know that once the rock started to cool, weathering could begin. So our first sedimentary rock is now on our radar screen. So island arcs are starting to get formed, and now they're subjected to elements of weathering. And as that occurred, that produced higher percentage silica-based minerals in the weathering process naturally. So when mafic rocks were melted at subduction zones, this added a different chemistry mix to the mill. And that meant that the island arcs should become less ultramafic and getting more on the higher silica side. Over time, that's going to create a distinctively different type of crust from the initial crust, which will be continental crust. Protocontinents were formed as island arcs accreted together along their margins during these subduction zones, and we had a few continental masses that were made by the end of the Hadean. Do we have an accurate record of what those look like? And the answer would be no, because we have virtually no rock record of the Hadean. However, we do have a very good rock record of the Archean. Early Archean rocks are highly deformed and very difficult to find. They're metamorphosed substantially from pressure and from heat, so most of them are difficult to interpret at best. Later Archean, not so much so. We have some pretty good rock record of them, but some important events occur during the Archean. The first is the shield rocks form, and we'll talk more about what those are in just a minute. The shield essentially is the basement rock. This is the initial material of the continents, in other words. It's the cores of continents that began the oldest material. The platforms are those rocks that are Precambrian that get covered by sedimentary rocks. In other words, they are the rocks that cover the shield, so the shield's buried beneath them. Sometimes the shield is actually exposed at the surface where you can see Precambrian rock. And then the cratons are added with the shield and the platform together, and typically cratons encompass all rocks, including newer sedimentary rocks that appear on the radar screen, other igneous and metamorphic rocks that may occur on continents. Another very newsworthy event for the Archean is we get our first life form. I'm not here to define exactly how that life form came to be, But we will have some discussions on that. And I want your thoughts on that in discussions when we do have it, because this is a very, very controversial issue. It's a huge miracle in the rock record, no doubt. How do you go from nothing to something? But the first prokaryotes, single-celled organisms, appeared very early on in the Archean. So let's talk more about that craton. All continents have a huge, vast area of exposed ancient rock material that are referred to as the Precambrian shield. So in this case, this is all red would make up the craton. Well, the shield part of the Canadian shield's right in here. So extending from the shield are buried Precambrian rocks that are called the platforms. And if you were to dig down through those sedimentary and other rocks above it, you would ultimately hit basement rock. The adjacent rocks to the buried Precambrian rocks are referred to as the craton. So the craton extends all the way out from the shield as far out as the edges of the original continents would go. So these are the original continent nuclei or shapes. Everything that you see in green in this picture are add-ons. So you need to think about that for a minute. Most of the continent that we think of are add-ons, and even down here in the south where it shows red, most of this is add-on too from other locations that got squashed in. But look at all of our margins on the east and west coast, for sure add-ons. So little deformation has happened in the interior sections here to rocks, but lots of deformation has occurred along orogenic belts here and here. Initial cratons are going to gain size because they get smashed by other things, other continents that have been rifted apart, or island arcs that come into the continents, and that's a huge theme during the Paleozoic, by the way. And ultimately, they're going to gain size. So North America is made up of multiple different types of cratons. They're all stuck together like a puzzle piece. And that is described as one big large unit known as the Canadian shield. This represents the exposed part of the craton that is Precambrian in age. Where can you find rocks like this? Very commonly around the Great Lakes region. New York City even has it. Greenland is almost one solid Precambrian mass, and northeastern Canada. Only 22% of the Earth's exposed Precambrian rocks are Archean in age. Most of those are going to be in the form of what we call green belts and granite gneiss complexes that were commonly created as we got island arcs that squashed into our newly formed cratons. So the likely source of granite comes from plutons that were created in island arcs, and as they subducted against our continent, those would create volcanoes, which would allow us to get almost long stripes of these variety of different chemistry rocks, otherwise known as green belts. So when we look at greenstone belts in particular, they are divided into 3 parts, with the lower and middle sections being volcanic and the top section representing sedimentary deposition that occurred during the Archean and some even during the Proterozoic. The greenstones are usually found where you have rock deformation like synclines, and the greenish minerals are formed during low-grade metamorphism. So you get the original craton that gets squashed, and you get some metamorphism that occurs. Another thing that's common in green belt geology is the presence of pillow basalts. From physical, you should remember that pillow basalts come from subaqueous volcanic activity, like volcanic seamounts up and down the sides of those, where the lava coming out at the bottom of the ocean hits the water and cools into these globular shapes called pillow basalts. So you'll see both of those types of things, green minerals and pillow basalts, in green belt stone type environments. Comatites are the lava flows that were created back in the Archean. Now, we don't have these lava flows as igneous rocks anymore. If they're available, they've been metamorphosed. We can even see a little bit of pyroclastic materials found in some of these early ultramafic lavas, which you would not expect to see much of at all, indicating there was some blending going on. These lavas mainly occur in Archean rocks and rarely occur in Proterozoic. So what happened was the Earth started to cool off. And we made cranking out continents big time during the Archean, still cranking them out during the Proterozoic, but at a slower rate. We make none of this type of material today because the radiogenic heat from the Earth's interior is just not hot enough to produce ultramafic rocks that need a surface temperature. That's not a subsurface, but that's a surface lava temperature of greater than 1600 degrees Celsius. So that's pretty darn hot. This is an example of metamorphosed comatites that are found in Canada. So if you recall to the sedimentary section of green belt stones, this is the upper regions of Archean green belt areas. And they're made up of two dominant rocks in the sedimentary section, gray rockies, which are sandstones that have both small grains and big grain fragments of sands, and then argillites, which are metamorphosed shales that have just slightly been metamorphosed. Rocks that are found in these types of environments also show indications of being impacted by turbidity currents, which also shows us that there were rivers in place. They show small-scale cross-bedding in tune with fluvial deposition and even graded bedding. So we know by the Archean we started having river systems in effect and oceans that could produce graded beds as well. So how old are these green belts that we find? This is what greenbelt rock tends to look like, and the oldest greenbelt rock that we have is 3.6 billion years old. So we know starting about that far back in South Africa, we were cranking out continents and cores of continents in a pretty fast manner. When we look at the oldest rocks in North America that are greenbelts, they're found in Canada, and they're metamorphosed comatites, schists, quartzites, and even banded iron formation, which we'll get to a little later. So our craton has a lot of greenstone belt rocks in them, but primarily found in the Canadian Shield. You can see some up in Michigan, Minnesota, and even in Wyoming, believe it or not. The origins of green belts have a fascinating story. They're thought to have come from an island arc, and as the island arc is pushed by some kind of mid-oceanic ridge towards a continent, the back arc, meaning the back side of that particular volcanic arc, gets squashed up, these sediments that have accumulated here, and these turn into being almost stripes against the continent as this thing accretes onto it. So greenstone belts are likely originated in the back arc basins of island arcs, and that would look much like the Sea of Japan today. So a basin would lie between the volcanic arc and the continent and be closed up as the volcanic arc is consumed at the subduction zone, and some of it accretes on to the continent. So greenstone belts appear in parallel layers as these representing accretion events along the edge of a continent. So green belts are very special to Archean, and they are associated with Archean geology, so keep that in mind for your test. We know that sometime during the Archean, plate tectonics was well underway, and that plates were moving around fairly quickly as compared to what we'll see in Proterozoic and certainly during the Phanerozoic. We had a higher radiogenic heat left over from the Hadean, and through the Archean that would cause continents to move at a much faster rate. We would have had hotter volcanoes, hotter lava flows, but by the end of the Archean we know that we had cranked out at least 30 to 40% of the present continental crust that we see today across the globe. So that's pretty impressive, busy time for creating continents back in the Archean. Probable fossils begin to have the right conditions to form as far back as 3.8 billion years ago, and should have been appearing in the rock record by 3.5 billion years ago. So geologists look for rocks, even if we think that we haven't found them yet. We know that there should be rock evidence of this. We can tell you for sure that we find evidence of fossils that date back to 3.0 billion years ago from abiogenesis. So that life form that started forming in that manner would have took several steps to get to that location evolutionary wise. So we need to look at the process of abiogenesis, and talk about how the first organism would have come to be. It's thought that the first organisms were single-celled cyanobacteria, and that's essentially what stromatolites are made out of today, is cyanobacteria, blue-green algae. And these are fossilized stromatolites from the Proterozoic, not the Archean, but we know we see our first stromatolites during the Archean. So bacteria are our simplest forms of life, and they can exist for long periods of time where they show no signs of living. They show no signs of existence in specific conditions, environmental conditions. Appropriate chemical elements would need to be in the environment for organic molecules to synthesize, such as carbon dioxide, water vapor, nitrogen, methane, which were all present in our early atmosphere that started to form during the Hadean. So how would these things synthesize in the first place? That's a good big question when it comes to the origins of life. Typically, you're going to need some type of trigger mechanisms to make the first monomers, which are going to be amino acids. Some kind of electrical spark, such as lightning, ultraviolet radiation, combination thereof. So simple organic molecules have got to synthesize in order to make organics work and start to create amino acids. Laboratory experiments have done just that. They've created synthesized amino acids, to be exact, 200 of them. So all they did was brew the right chemistry with the right conditions and created polymers. So nucleic acids and proteins get linked together to make polymers, and the big question comes, what steps occurred to make the monomers become polymers? If we can answer that question, then you know how life began to form. What we do know is that we were able to synthesize it in a test environment, in a laboratory, to make the goo turn into something organic. What we're missing is the time factor that it took to make this process occur geologically. One area we think this could be possible is hydrothermal vents, known as black smokers. Hydrothermal vents are thought to be places where polymerization could take place. Amino acids have been detected in some black smoker emissions. Of course, there's some controversy here that the conditions would be anything but optimal for life to start to originate. And then other thought processes are they're perfect conditions for life to originate. So many scientists think that hydrothermal vents were actually the starting place for polymers to start to form and amino acids to start to do their thing. Our first life is cyanobacteria, and these are photosynthesizing organisms, which are important because if they're photosynthesizing, that means they're going to have ample source to sunlight. Our earliest life forms did not have free oxygen in water or in the atmosphere to survive. So they would have had to be in the water and shielded from ultraviolet radiation in order to survive. While we don't have any known fossils for the first life, we can predict some of what they would have needed in order to survive. Adenosine triphosphate, ATP, is thought to be the nutrient source of our first prokaryotic cells. And so this type of environment would have clearly existed in the Archean type of situation that we would have had in the ocean. Our first life that we can attribute and find in the fossil record are actually stromatolites. They're algal reefs, so they look kind of like coral reefs, but they're made out of algae mats that are sticky, alternating layers of blue-green algae and sediments that have been glued together, such as these stromatolites from Glacier National Park. South Africa wins the gold prize for having the oldest known stromatolites found to date at 3.0 billion years of age. We estimate that stromatolites should date back to at least 3.5 billion years of age because the conditions were right starting 3.8 billion years ago. And we find rocks that show that evidence of chemical optimism all the way back to that date in Greenland. So geologists were now looking at the Archean resources that we have in terms of economic gain. No doubt that the massive production of continental crust produced us some extraordinary resources of ore, being metal. Gold and platinum would rank as the top types of things that are out there for Archean aged rocks. Chromium is another. 1/4 of the Earth's entire chromium reserves come from greenstone belts associated with Archean events building our continents, from ancient island arcs that are back arc basins, if you recall from our lesson. Pegmatites within granitic plutonic structures also contain valuable gemstones, valuable resources, and rock material that we use for building materials as well as for intrinsic value. Up to 8% of the banded iron formations around the world are known to be Archean. Could be even slightly less than that. It depends on what documentation you read. Most of our banded iron formations are found in the Paleoproterozoic, which will be our next lesson. But I wanted to take a few minutes to apply what you know and talk about the Grand Teton Range. While we'll revisit this a little later in the semester regarding the geology of the Grand Teton Range, I want you to recognize that the roots of this mountain are actually very much Archean in age. So let's visit that now, and we'll talk about what that looks like. See you in a few minutes. Bye. I am in Grand Teton National Park. This used to be a fairly small park, and Rockefeller bought up a whole bunch of acres, like 31,000 acres, from private landowners to give to the government to make this a bigger park, and this is one of his favorite areas, so it's a historic landmark. In addition to that, it's a really good view of the range itself, and I want to talk about the features that you're seeing in the mountains. First of all, the mountains are extremely old. They are Precambrian in age, about 2.7 billion years old. So they're made up of primarily granites. There's some gneiss in the basement rock as well. And then there's some intrusions of diabase that are out there from more recent volcanic eruptions about 700 million years ago. What you can notice is the distinctive shapes of all of those mountains came from glaciers. You see U-shaped valleys, arêtes, horns. There are even some modern-day glaciers. I will zoom on one right now. This is called Teton Glacier right there. There's like a moraine deposit, by the way, that's just down from there. The big valley that's green, that was actually the site of a very large glacier that was here during the last ice age, where these valley glaciers from the mountains poured into, and it extended just south of Yellowstone all the way to Jackson Hole, Wyoming, which is about another 30 miles or so from here. So it was a fairly large structure, and it laid down a lot of moraine deposits, which was responsible for making these glacial lakes. You can see it's getting kind of busy here, so we're going to sign off, and we'll see you at the next stop. So you've just learned about the Grand Teton Range. You learned that it's around 2.7 billion years old, and that it's made up of these really deep-rooted gneisses and granites and even schist. Interestingly enough, the Native Americans of this area used some of these rocks to make their bowls out of. And this material is a very durable, old Precambrian rock. Now, the shape of the mountains that you see today is a much more recent geologic story, which is the reason I wanted to show it to you, is just to remind you that what you see didn't happen all at once. Geology is a process, and you have to look at the clues, and one clue would tell you, hey, this thing just got made by all these glaciers. Well, that's true, but the reality is a bulk of what happened that made this rock happen way back when in the Archean eon, and we've had a series of interesting geologic circumstances that have changed the Grand Teton Range from what it is today. So if I could encourage you to get to this park at some point in your life, you will not be sorry that you went. Not only is it stunningly beautiful and the wildlife's incredible, it's serene. and it's a beautifully kept landscape that represents a time in our history, even as a nation, where we were protecting some of these really grand places like the Grand Teton Range. It also represents a chunk of geologic time with a series of evolutionary events that caused it. So we're going to show you a quick video of the national park system that they put together, that there's a YouTube video for you to watch. There's no narration, but it's there to kind of show you the events that happened over geologic time. I'll see you for the next lecture on Proterozoic. Bye.